Hello everybody, this is Dr. Eldek and today we'll talk about chapter 2 in the semiconductor devices. It is about PN junction or diodes. Remember in chapter 1 I talk about the P-type and N-type, and if we have only PN, P-type or N-type by itself will not be useful. But if we have them together, then in this case we can make a device that can do a lot of applications. So this chapter here, we have the first element is called here PN junction. What's a PN junction? PN, from the name, it is P, which is P-type, and N, which is N-type. So imagine that we have, for example, here this is a P-type, and this is N-type. In P-type we have extra hole, and in N-type we have extra electron, or extra holes and extra electrons. So what happened? That we'll have in this region here, in this line between them, you will have the electrons will move from this side to this side to fill the holes. So again, all these electrons will go to fill the holes. This is what happened when we have P and N beside each other. So in this case, we will have, for example, the electrons from here will move to this one, and the electrons here move to this one. But this one here, oh come on, this will take some time here. If you want to move this one to this one, now it will be difficult. But it will be easy to move the electrons adjacent to this line. So what happens that after a while, you will have an area that's full of electrons. The holes are filled with electrons. Okay, so in this case, if you wanna, for example, move this electron to this side, then in this case it has to pass this region here that filled with holes that has electrons already. So this is what we call it here depletion region, or a barrier region. So again, the electrons in from adjacent to this line is very easy for them. This one can move here, this one can move here, and so on. But at certain time when you have a far electrons, it will be harder for them, and so on. Then after a while you will have a region where it will be difficult for the electron to move from the N-type to the P-type, and this is what we call a depletion region. Okay. So imagine now after that we apply a certain voltage on this PN type. What happened? What happened if we imagine that we have, for example, a positive voltage here and negative voltage here, or the opposite? What will happen? See, this is what we will see in the next slide. If we imagine that we have this battery here connected, so the positive is connected to P and the negative is connected to N. Then in this case, the positive will be pushing this positive here. Positive and positive, there's a repulsion here. Then the positive will give a power to this one here to move to the other side, and the negative will push the electrons to move to the other side. Okay, this will not happen, of course, if this voltage is very low voltage. So imagine that you have very low voltage, then in this case you can't push the electrons to move from here to here. But a certain value, assume that the voltage, for example, is 0 volt and then 0.1 volt, 0.2 volt, a certain voltage. Okay, then in this case it will be this voltage is enough to push the electrons, okay, from the N-type to the P-type through the depletion region, through this depletion region. And this is what we call it here. This is a barrier potential or forward voltage drop. And this voltage is different from one material to another. So if it is silicon, for example, it's 0.7 volt. Germanium, it is 0.3 volt. For some other, for example, what we call it here, PN junctions, I call it LED. This is a light emitter diode. This is 1.5 to 3 volt, depending on the color. Okay. So here, imagine that this is a high voltage. Now, what happens that we have electrons moving in this direction. So it will be exactly as if you have a short circuit, as if we have a short circuit. If we exchange the polarity, so if we have a negative here and positive here, what will happen? We have something called the reverse bias. So here, this is a forward bias. If we have a positive connected to positive and negative connected to negative, this is a forward bias. The PN junction is acting as a short circuit. But if we reverse it, we call it a reverse bias. And what we expect? We expect that we have open circuit instead of short circuit. So here, imagine that we have this as a positive connected to the negative, and the negative is connected to the positive. So what will happen? Initially, we'll have some holes, for example, here will move to the electron, so to the negative. Okay, and also some electrons will move to the positive. Okay, some of them. So this will create some initial current, just temporary current. This is a very small current, just temporary, and then after that will disappear. But after that, of course, this is exactly as if you are attracting the negative to negative and positive to positive. This means that you increasing the depletion region. So imagine that the depletion region is like this. Okay, so now the negative side will attract, well, the positive side will attract the electrons, then it will push it like this, and the negative side will attract the holes, then it will push it like this. Then actually you are increasing the depletion region, so you are making more, having current is impossible. So it's exactly like open circuit. So this is what we call it here, reverse bias. So when you have a reverse bias, you have almost an open circuit. The relation between voltage and current in the p-n junction is explained by what we call it here, Shockley equation. So the current equal what? Equal Is. This is the reverse current. As I said, this is just temporary current, very small current. Time e to the power of Vd. This is the voltage across the diode or p-n junction. And time q. Q is the charge of electron. N is a quality factor, and this is number between 1 and 2. And K is a temperature. K is a Boltzmann. Is a Boltzmann constant. Okay, this number. And T is a temperature. T is a temperature. Then all minus 1. And when you plot this equation, if the voltage is positive, this is a forward bias. If the voltage is negative, this is a reverse bias. So as you see here, the voltage, when the voltage is positive, then you don't have any current. There's no current. There's no current until you reach a certain value where the voltage can overcome the depletion region. Then in this case, it will act almost as a short circuit. You have a very high current now. Okay, this current, of course, can be limited by adding resistor, but you will have a high current, which is almost constant here. Then the voltage will remain almost constant. As I said, it is 0.7 volt for silicon, 0.3 volt, 0.3 volt, I believe, for I can't remember, but anyway, 0.7 for silicon, 0.3, 1.5 to 1 to 3 volt for LED with different colors and so on. Okay, and in the reverse bias, if it is negative, you do not have a current. The current is just Is. This Is, as I said, this is just temporary current, very small current. Okay, and it's very small, and at certain voltage, if you have a very high voltage, okay, this is the reverse voltage. As I said, it is open circuit, but at certain time, if this is very, very high voltage, then you will have a breakdown voltage like this. Since the current, it will break the p-n junction and it will act as a short circuit again. Okay, so this one here, we don't want to reach this. We always need the p-n junction to act as a open circuit, then you don't have current, or a short circuit when you have forward bias. This is what we need to do. As these are some types of diodes. So this is how it look like. This is the p-n junction. This is a symbol over the diode. So this is P, and this is the N. This is a positive. This is a negative. Okay, for this symbol for the diode, you see they have a black line here, small area here, black. So this is the N. Here is the same. Here it is silver. Okay, so all of them here, this is the N type, the N, and this is the P. This is the P. This is how the diode look like. So we represent this figure here. This figure can be can say this is approximated in 3 methods. So as you see here, this is a forward and this is the reverse. So how it look like? This is just ideal that we don't have the forward bias voltage, so we neglect the 0.7 volt for silicon, for example. We assume that it's very small, 0. So if we have a high voltage, for example, 10 volt, 20 volt, so 0.7 is negligible with respect to this voltage. If this is a forward bias voltage, for example. So we do not consider the 0.7 volt. So we assume that the voltage across the diode is 0 in the forward bias to have a current. But in the reverse, we do not also assume that we have this IS. We neglect it. So we have a open circuit, completely open circuit. So this means that in the ideal case here, the diode is acting as a short circuit, completely short circuit in the forward bias, and completely open circuit in the reverse bias. So it's acting as a switch. If you have a positive voltage, forward bias, it's short circuit, so it's connected. If it is reverse bias, open circuit, so it is actually open, so there is no current. So it's acting as a switch, on off, without any voltage or anything on it. The second model here, which is this one here, we assume that we have a voltage. So this is VF, and we assume that this is constant. Like for example, it's 0.7 or so. So in the forward bias, the current is 0 until it reaches VF. Then after that, the voltage across the diode will be this VF, which is 0.7 volt, for example. The third one, which is the most accurate one, is that we have in the forward bias here, the current will be 0 until it reaches this VF. Then after that, it will increase. Okay, there is a relation between the current and voltage related to this called R bulk here. This is the resistance of the diode. So if you look at this one here, the previous slide, it is almost linear here. It is linear. So the current over the voltage, or voltage over the current, is called is a resistance here. Call it R bulk. Okay, so you can use any of this. Usually we use this one here. This is the most famous one because we assume that the voltage is constant, 0.7 volt, for example.